All right, so this is the business calculus video for section 3.6. This is the third video. All right, so in this one, we're going to talk about what we call related rates. So sometimes both variables in an equation will be functions of a third variable, usually t for time. So for example, for a seasonal product such as winter coats, the price P in weekly sales X will be related by a demand equation, and both price P and quantity X will depend on the time of year. So if we differentiated both sides of that demand equation with respect to time, it will give an equation relating the derivatives dP over dt and dx over dt. So these related rates equations will show how fast one quantity is changing relative to another. Okay? And before we jump into some other examples, let's start with an everyday example. So look at example 6. It says a pebble thrown into a pond causes circular ripples to radiate outward. If the radius of the outer ripples is growing by 2 feet per second, how fast is the area of its circle growing at the moment when the radius is 10 feet? So we want to know how fast is the area growing. So that gives us an equation to start with. The area of equation of a circle. A equals pi r squared. And how fast, that phrase right there, how fast is something changing, tells us that we're going to have to take a derivative. And if I take the derivative with respect to time of this function, I end up with dA over dt, because the derivative of a would just be 1, equal to 2 pi r dr over dt. Well, I need to now figure out what is dA over dt. And if we go back to the problem, you can see different parts of the r and the dr over dt are given to us. We want to figure out how fast this is growing when the radius is 10 feet. There's our r. We also know that that radius is growing at 2 feet per second. That is our dr over dt. So I can plug these in. dA over dt is going to be equal to 2 pi times 10 times 2, which would give us 40 pi, or 125.6. Right, so what this tells us is, therefore, at the moment when the radius is 10 feet, the area of the circle is growing at the rate of about 126 feet per second. Feet squared per second. All right, so when the radius is 10 feet, the area is growing at a rate of 126 square feet per second. So we took an equation that had two different variables, took the derivative with respect to time, and then we're able to plug in and find an answer. All right, so how do we do this all the time? So to determine the quantities, to solve a related rate problem, the first step is to determine the quantities that are changing with time. Step 2 would be to find an equation that relates these quantities. Sometimes a diagram is helpful. Step 3 would be to differentiate both sides of the equation implicitly with respect to t. Then 4, substitute into the new equation any given values for the variable and for the derivatives. A lot of times these are going to be given in the wordy part of the word problem, so go back and read all that. Read it again if you're not sure where all the numbers fit. Then we're going to solve for the remaining derivative and interpret the answer as a rate of change. So let's look at example 7. Said a boat yard's total profit from selling X outboard motors is P equals negative X squared plus 1,000X minus 2,000. If the outboards are selling at a rate of 20 per week, how fast is the profit changing when 400 motors have been sold? Sorry. Okay, so how fast is the profit changing? That means I need to take this function and find the derivative. Profit changing would be your dP over dt. We know that 400 motors have been sold. There's your X. And they're selling at a rate of 20 per week. That per week gives us dx over dt. So I'm going to take my function, P equal to negative X squared plus 1,000X minus 2,000, and take the derivative. The derivative of P would be dP over dt equal to negative 2x dx over dt plus 1,000 dx over dt. Once you've taken that derivative, that implicitly take the derivative, you're going to plug in all the numbers that you have. Okay? So I want you to take and plug in the numbers that were given and see if you can come up with a sentence that tells what this is talking about, and then come back and check your work. Alright, so if you plug in all the numbers, we end up with dP over dt is equal to 4,000. This means that the company's profits are growing at a rate of 4,000 per week with the given specifications. Alright, let's try one more. Okay, so in this one, we weren't given all the numbers outright. We're going to have to find some things. So let's read it. We have a study of urban pollution predicts that sulfur oxide emissions in a city will be S equal to 2 plus 20x plus 0.1 x squared tons, where x is the population in thousands. The population of the city T years from now is expected to be x equal to 800 plus 20 square root of T thousand people. So we need to find how rapidly the sulfur oxide pollution will be increasing 4 years from now. So I'm going to take this function and I need to figure out how fast that population is growing. When I take the derivative, I know I'm going to need a ds over dt, an x, and a dx over dt. Okay, well, I'm going to be able to find ds over dt, but I need these other two pieces of information. What I was given was an x. I'm given an equation for that. X equals 800 plus 20 square roots of t, or 20 t to the 1/2. So part of my problem is done. Now I need to find dx over dt. And I can do that fairly quickly by taking the derivative of the x function that I was given. And we're going to end up with the derivative of 800 is 0. The derivative of 20t to the 1/2 gives me 10t to the negative 1/2. Okay, I'm going to pause the video, take a second, and find what the numerical value is for x and dx over t, given that we're dealing with 4 years from where we are now. Okay, so if you plugged in forward the x equation and the dx over dt, you should have gotten x equal to 840 and dx over dt equal to 5. So now we can go and find the ds over dt, which is what we need. So I'm going to take the s function, s equal to 2 plus 20x plus 0.1 x squared, take the derivative, and then plug in the given values. Okay? Again, I'm going to pause the video. I want you to take this derivative, plug in the numbers that you know, and then see if you can find and interpret the answer. Alright, so if you take the derivative of the s function, we end up with ds over dt equals 20 times dx over dt plus 0.2x times dx over dt. By plugging in all the numbers that we know, x equal to 840 and dx over dt equal to 5, we end up with the number 940. What this means is, in 4 years, the sulfur oxide emissions will be increasing at the rate of 940 tons per year. Now, I did mine in a different order than the book did, okay? This is how it made sense in my head in the order that I needed to work it. So, if you look back at the book, it's a little bit different order. So, if this didn't make sense, definitely go back and read the example in the book. Again, as always, if you have any questions, please let me know.